Hi everyone. Today we are going to discuss about orthogonal projections. In the last few classes we have discussed about positive operators, self-adjoint operators, normal operators and unitary operators. So let us start with the definition. Let P be a bounded linear map defined on H. Then P is said to be a projection if P square equal to P. So this is also known as an idempotent. Okay, so let us look at a simple example. So define P1 from R2 into R2 by P1 of x1 comma x2 equal to x1 comma 0 for all x1 x2 in R. Then we can easily show that this is an idempotent or it's a projection. Similarly define, so we can define P2 of x1 x2 as 0 comma x2 for all x1 x2 in R. Now if you look at P1 plus P2 of x1 comma x2 is nothing but x1 comma x2 for every x1 x2 in R. So we can again check that P2 is also linear and both P1 and P2 are projections and their sum is identity operator. Identity on R2. Let us look at few more examples. So define P1 from R3 into R3 by P1 of x1 x2 x3 as x1 0 0 for all x1 x2 x3 in R. So we can show that this is again linear and this is also bounded and it's a projection. So similarly define P2 of x1 x2 x3 as 0 x2 0 for all x1 x2 x3 in R3. And similarly we can define P3 of x1 x2 x3 as 0 0 x3 for all x1 x2 x3 in R3. So we can check that P1 P2 P3 are bounded linear maps. In fact norm of each of these things are 1. So Pj in B of R3 and norm Pj is 1 for all j equal to 1 2 3 and Pj square is Pj for all j equal to. So these are all projections or idempotents. Now if you look at these two examples, range of P1 and range of P2 are orthogonal to each other. In the first example case, range of P1 is the x-axis, range of P2 is the y-axis, and similarly In the second example case, range of P1 is x-axis, range of P2 is y-axis, and range of P3 is z-axis. That means all the ranges are orthogonal to each other. And not only that, so we can easily see that null space of Pj is orthogonal to range of Pj for all j equal to 1 to 3. For example, null space of P1 is the yz plane, whereas null space of P2 is the xz plane, and null space of P3 is xy plane. So in each of these cases we can conclude that null spaces are orthogonal to range. Let us look at one example where this condition is not satisfied. Define Q from R2 into R2 by Q of xy as x comma x for every xy in R2. We can easily check that this is a linear map, and we can also check that this is bounded. So Q is linear, that is very clear. And if you look at norm of Q xy, so whenever we discuss about R2 or R power n or C power n, we can look at the Euclidean distance or Euclidean norm only, and the Euclidean inner product in this case. So all the time we use that convention. So norm of L2 norm of Qxy is nothing but L2 norm of x comma x. This is square root of 2 mod x square. This is square root of mod x, and we know this is less than or equal to square root of mod x square plus mod y square power 1 by 2. So that means square root of norm of xy. So we can conclude that norm of Q is less than or equal to root 2. So can we say that norm of Q is exactly root 2? In fact, we can say that Q of 1 0 if you take norm, this is L2 norm of this is 1 comma 1. So this is exactly root 2. So therefore we can say that norm of Q is exactly root 2. Okay, so this is we can easily show that this is a projection. So we can easily check that Q square equal to Q. If you look at the kernel of Q or null space of Q, so we can null space of Q is set of all xy such that Q of xy is 0. That means set of all xy such that x comma x is 0, that is x is 0. So y axis is the null space in this case. So this is the null space, and range space is the line y equal to x. This is range of P. So null space of P and range of P are not orthogonal, but this is a projection. So in general, for a projection, null space and range space need not be orthogonal. Okay, so let us look at some important observation about projections. Let P be a bounded projection which is non-zero. Then we have the following. Then I minus p is also projection. So to look at this, I minus p square is I minus p into I minus p. This is I minus p plus p square. This is I minus p plus p, because p square equal to p. So we can say that this is I minus p. If p is a projection, I minus p is also projection. Other way also true. If I minus p is a projection, I of I minus p is a projection. That means p is a projection. So we can show that, we can conclude that p is a projection if and only if I minus p is a projection. So this is the conclusion. Second one, if p is a projection, we can show that range of p is always closed. Range of p and null space of p are closed. So null space is closed because p is a bounded operator, but range of I minus p we can write as, range of p we can write as null space of I minus p. So this is set of all x in such that I minus px is 0, that is px equal to x. So this is trivial. So since I minus p is a idempotent or projection, so this is closed, hence range of p is closed. Okay, so we can also observe that range of I minus p is nothing but null space of p. This we can easily prove using the same trick that we used above. Okay, if p is a projection, we assume that p is a idempotent which is non-zero, so we can say that norm p is bigger than or equal to 1. So that is because, so we have norm of p is nothing but norm of p square. So this is less than or equal to norm of p into norm of p, that is norm p square. So this implies that norm p into norm p minus 1 is bigger than 0. So this implies that norm p should be bigger than or equal to 1, because norm p cannot be 0. We assume that p is non-zero. So whenever p is a projection, we can write h can be written as range of p direct sum with null space of p. So note that this is not an orthogonal direct sum, it is just direct sum. So this is easy to prove. Let us take x is in h, then x can be written as I minus px plus px. Now we observe that this element I minus px is an element of range of I minus p. So this is in range of I minus p, but we have observed that this is exactly null space of p, and anyway this is element of range of p. So h can be written as range of p plus null space of p. Next we want to show that their intersection is 0. Claim range of p intersection null space of p is 0. So whenever x is in range of p intersection null space of p, so when x is in range of p, x equal to py, for some y, and Px is 0 because x is also in null space of P. So from this we can say that P of Py, that is P square y, that is Py equal to 0. So this implies Py is nothing but x. So we have shown that this decomposition is exactly direct sum decomposition. We can write H as direct sum of range of P and null space of P. Okay, so these are a few important observations regarding the projections. Next we discuss about orthogonal projections. So a projection is said to be orthogonal if the null space and the range spaces are orthogonal to each other. So definition: a projection P is called an orthogonal projection if null space of P is orthogonal to range of P. So we have seen earlier that if P is a normal operator, then the null space and range space are orthogonal to each other. So let me make a remark. If P is a normal projection, then null space of P is orthogonal to range of P. So that means we can say that P is orthogonal. So we have seen several examples earlier. If you look at the earlier examples, in the first example P1, P2 are orthogonal projections, and here in the second examples P1, P2, P3 are orthogonal. And if you look at the Q that we have defined in example 3, and we have clearly seen that null space of P and range space of P are not orthogonal to each other, hence Q is not an orthogonal projection. Okay. So we can now what is the advantage of having orthogonal projections? What is the difference between usual projections and orthogonal projections? So we will see the difference now. We can write as a theorem. Let P be a non-zero projection, be a projection, then the following are equivalent. P is orthogonal, second one is P is positive, that is inner product of Px with x is positive for every x in H. The third one is P is self-adjoint, and The fourth one is P is normal. So we have observed that when P is a normal projection, then it must be orthogonal. That means 4 implies 1 holds. So let us look at the proof. When P is positive, automatically it is self-adjoint. When it is self-adjoint, automatically it is normal. Hence 2 implies 3 and 3 implies 4 are clear, and we have already observed that 4 implies 1 is also true. Now only thing we have to see is 1 implies 2. Suppose P is orthogonal. Let us take x is in H, then we can write x as u plus v, where u is coming from null space of P and v is coming from range of P, and u is orthogonal to v because it's orthogonal projection. Null space of P and range space of P are orthogonal to each other. Now consider, so we want to show that P is positive. So for that we have to look at inner product of Px with x. Now this is nothing but inner product of, so Pu plus v. Pu is 0 because u is coming from the kernel. This is Pv and here x is u plus v. Now so Pv inner product with u plus inner product Pv with v. Now Pv is an element of range of P and u is an element of null space of P, so they are orthogonal. So this is, the first term is 0, so you will get Pv and v inner product. Now whenever we have an element in range of P, then we can say that Pv equal to v. So v is in range of P implies v equal to Pw for some w h. So this implies, now Pv is P square of w, but P square is P, so this is Pw, that is v. So that means whenever we have an element from the range of P, so that element remains as it is when we apply P. So from this we can say that so we can conclude that inner product of Px with x is nothing but inner product Pv with v, but we know that Pv is nothing but v, inner product v with v, so that is always positive. So this completes the fact that, proof of the fact that P is bigger than 0, P is positive. Okay, so this is one of the important characterizations of orthogonal projections. So in general, a normal operator need not be self-adjoint and a self-adjoint operator need not be positive, but in the case of orthogonal projection, all the concepts coincide. Okay. Now one more important observation is that if P is an orthogonal projection, we can say that norm of P equal to 1. So if P is a projection, we have concluded that norm P is bigger than or equal to 1. But if in particular P is an orthogonal projection, we can say that norm P is 1. If P is an orthogonal projection, then norm of P equal to 1. So let us take x in H, then we can write x as Px plus I minus Px. Now Px is coming from the range of P, I minus Px is range of I minus P, that is in null space of P. So this is an element belonging to null space of P, and this is an element belonging to range of P. Now if you compute Px, so this implies Px is P square x, and P of the other one is 0, so this is again okay. Okay, so now if you look at so this implies norm of x square is nothing but norm of Px square plus norm of I minus Px square. So this is bigger than or equal to norm of Px square. So this implies norm of Px square is less than or equal to norm of x square for every x in H. So here we have used the Pythagorean property. Because Px and I minus Px are orthogonal to each other, we can use the Pythagorean property. So from this we can conclude that norm of P is less than or equal to 1. But we know that already norm of P is bigger than or equal to 1. So as we have so we can conclude that for an orthogonal projection, norm is always 1. Now can we say the converse is also true? So the question is the following. So we can ask, is the converse true? So the question is the following. Let P be a non-zero projection such that norm of P equal to 1. So is it true that P is orthogonal? In fact, the answer is yes. So I suggest you to work out the details. That means this is also one of the characterizations for an orthogonal projection. So we have given earlier 3 characterizations. Now this is the 4th characterization of an orthogonal projection. Now we can ask the question, is it possible to get an orthogonal projection in Hilbert space? So we can actually get an orthogonal projection in a given Hilbert space by the projection theorem. Let us look at this part. Let M be a closed subspace of so this is a proper subspace. Then we have H can be written as M direct sum M per, here it is orthogonal direct sum. So this is the projection theorem. That means if x is in H, we can write x as u plus v, where u is coming from M and v is coming from M per. Now we can define a projection. So define a linear map P from H into H by P of u plus v, write as u for all u in M. So every x can be written as u plus v. So we can write P of x as u. So in general, x also can be written as, so this can be written as u comma 0 plus 0 comma v, because M can be identified as M direct sum 0 as a subspace of H, and M perp can be identified as 0 direct sum M perp in H. So u plus v we can write as u0 plus 0v, so that is nothing but uv. So we have defined p of uv as u for every u in M, v is M perp. So it is easy to check that P is linear, and we can also check that it is bounded. So norm of PUV is nothing but norm of u, but this is less than or equal to norm of u square plus norm of v square square root of that. This is norm of uv. So we can conclude that norm p is less than or equal to 1, and here we can easily show that null space of P is exactly M perp and range of P is exactly M. So what we have obtained from this is that if M is any closed subspace of H, using the projection theorem, we have defined a map P like this, then we have got that null space of P is exactly M perp and range of P is M. So given any closed subspace, we can associate a projection whose range is exactly that closed subspace. And on the other hand, we have shown that range of any projection, in particular range of an orthogonal projection, is closed. So here in H we have taken a closed subspace, and in B of H we associated a projection. So this is a projection onto M. So P is called projection onto M. Onto M, and so we got a projection here. So this is denoted by the projection onto M with P suffix M. So this is the notation we will be using again and again. P suffix M is the orthogonal projection on H whose range is M. So let me summarize what we have done. We have taken a closed subspace in H, and we have associated with a projection whose range is exactly M. And if you have a projection, if P is a orthogonal projection, so then we can associate this to range of P, which is a closed subspace. That means we are associating a closed subspace with a projection and a projection with a closed subspace. So because of this correspondence, we can actually study about the closed subspaces using operators and vice versa. For example, using the convergence of operators, we can actually define convergence of subspaces. We can try to define the distance between two subspaces also. So let us take M and B closed subspaces. Define theta Mn as the norm of operator norm of difference of these two projections Pm and Pn. As I told earlier, Pm stands for the projection orthogonal projection onto M, and Pn stands for the orthogonal projection onto M. Now using this we can show that theta is a metric on closed subspace of H. So this metric is known as the gap metric, and using this metric we can discuss distance between two closed subspaces and convergence of subspaces to another subspace. So we can actually discuss about operators through subspaces and subspaces through operators. Okay, so this is about existence of a non-trivial projection when we have a Hilbert space. Okay, so one simple example let us look at. Let us take U is in H, U is non-zero. In fact, we can take norm U equal to 1. So define P from H into H by P of X, define inner product X with U multiplied by U for every X in H. Then we can easily show that P is an orthogonal projection. And norm of P is 1. Anyway, by showing norm of P equal to 1, we can conclude that this is an orthogonal projection. And range of P is spanned by single element U. So range of P is span of U. It's a one-dimensional space. So its dimension of range of P is 1. So dimension of range of P is known as the rank of the operator. So here this P is a rank 1 projection. So we discuss about rank 1 projections at a later stage. Okay.